We are thrilled to roll out the latest episode of the Quantum Seminar series dedicated to the research and academic quantum communities. The seminar takes place at noon Eastern Time and is hosted on the Qiskit YouTube channel. So if you're watching live right now, you're in the right place. My name is Olivia Lanes from IBM Quantum, and I'm very excited to be here today speaking with Bryce Fuller. So I will introduce Bryce now, and then we'll go ahead and get started. So Bryce Fuller is a quantum computing applications researcher, also at IBM Quantum. He joined IBM in 2019 after completing his bachelor's degree in electrical and computer engineering from UT Austin, where his focus was in data science and machine learning. Now he is focused on the design and practical implementation of quantum algorithms for machine learning and optimization, and he's also working on the changing landscape of software used to design quantum algorithms. In addition to this research, Bryce is also a subject matter expert on the IBM Quantum Prototypes team. So welcome, Bryce. We're super happy to have you here today and really excited to hear about quantum relaxations and apply composites.
Awesome. We'll get started. So this work is joint work that came out of a collaboration between IBM Quantum and Boeing. And I also wanted to call out that part of the slide deck was taken from Charles Hadfield's notes on this talk. So this talk kind of factorizes nicely into two different talks, actually. So there's this interesting algorithm that I'm going to speak mostly about. And then the second part of the talk is going to be focused on a specific use case in aerospace engineering. And so there will be two conclusion slides and we'll kind of break it up. Cool. And again, please ask questions in the chat if there's anything that's unclear. Happy to clarify. Okay, what are quantum relaxations? So I think it's better to start with what is a relaxation in general in the context of an optimization problem. So a nice example that I like to use is a problem called the MaxCut problem. It's very intuitive, right? So the idea is that you are trying to load a truck with boxes of different weights and sizes, and you have constraints on how much that truck can carry in terms of how big the boxes are and how heavy they are. And let's say you have tons and tons of these boxes and you're trying to figure out how to choose them to maximally fill this truck and be as efficient as possible. It's known that this is a hard problem. However, you can relax this problem to something easier, which was called the continuous MaxCut problem. So let's say I'm now allowed to cut these boxes into pieces. It's pretty clear that you can just always fill the truck. You know, you can just, whatever size you have available, you can slice up a package to fit into that space and you can always maximally fill it. The trick though, is trying to find relaxations such that solving the easier problem gives you some kind of information about the harder problem. And then you can use those relaxed solutions to get better solutions for your original harder version, right? So in this case, it's not clear that, you know, knowing how to slice up these boxes tells you anything about how to pick them in discrete numbers, right? So this is kind of going to be the framework. And yeah, and typically these relaxations are to easier problems, but in the quantum case, this will be slightly different. Something we'll talk about, right? So the problem we're going to be applying this to is MaxCut. And so it's not the knapsack problem. So I wanted to briefly review what MaxCut is for everybody, right? So the idea is you have some graph, which we define as a set of edges and vertices. These nodes are vertices and there's edges between them. And I'm going to have some binary values, mi, that I'm going to be assigning to these nodes, right? We're going to have them be plus or minus 1, but sometimes people have these be 0 and 1, right? And for, you know, the sake of just visualizing this, we can really just consider these to be colors, right? We're going to color our nodes into two sets, right? And what MaxCut cares about is looking at the edges that connect nodes of a different color, right? And so informally, the way you could state the MaxCut objective is that we want to figure out a way to color each of these nodes such that the number of blue edges is maximized, right? In other words, all edges between nodes of a different color will be cut, and we want to maximize the number of cuts we make, right? And it's known that solving this problem optimally is very difficult, difficult enough that we don't expect to be able to do it in any sort of reasonable time efficiently. So whenever we need to solve this problem in practice, we use heuristics, and this technique will be one such heuristic. Cool. So the main results for this first part of the talk on this algorithm will be that I'm going to propose a way to solve this problem using roughly a third of the qubits that you would naively need to use for existing optimization algorithms on quantum hardware. We're going to do this by embedding our solutions to our problem into quantum states using something called quantum random access coding, which we'll discuss. This is going to allow us to encode our problem into a relaxed Hamiltonian version of the problem. We can approximately solve this relaxed quantum version of the problem on a quantum computer. And then given the solution to that relaxed problem, we're going to try and get answers back to our original problem, right? So this was what we showed in the knapsack problem, where we're going to try and solve this relaxation and then use that information to get better solutions for the original hard problem, right? And we'll show that this procedure we present has a conditional lower bound on the approximation ratio you obtain from doing this. And we run this on hardware. So I'll show some results for this on hardware, and both for sort of a standard maximally difficult MaxCut instance. And then later on, we'll apply the same technique for a problem that's inspired by aerospace design. Great. Okay, so we have a lot to get through. So I want to quickly review how this problem is formulated whenever it's solved on quantum hardware, near-term quantum hardware, right? So QAOA stands for Quantum Approximate Optimization Algorithm, and it's often the reference that people use for these kinds of things. And the idea is that in QAOA, this is just for now visualizing what happens in regular MaxCut, right? We get some assignment of variables, some plus or minus 1, and then we have this objective function that tells us our MaxCut value. When we solve this using QAOA, we have this mapping from this bit string of plus and minus 1s to some quantum state, which I'm calling ket m. And I'm going to refer to this mapping as F0, right? And there's an analogous mapping that we can do over here on this objective function, which is showing that we can represent this objective function to our problem using a quantum Hamiltonian, right? So you can kind of see that there's some similarities here. We're just replacing our binary variables with some diagonal operators here, such that whenever you evaluate, this should be a density matrix here. Pardon that, it should be a bra as well. But such that when you evaluate this expectation value, it gives you the same objective value that you would have gotten if you had just evaluated this classically, right? So what this is showing is that QAOA has an embedding of our problem that faithfully represents the underlying problem that we wanted to solve initially, right? Okay, and so it will be useful later on to rewrite this state over here in a slightly more convoluted way. So it looks much more messy, and it is, but there will be parallels to how we represent this state and how we will be representing states moving forward. So I think this will be useful. Okay, so we're in search of a better encoding, right? On the previous slide, we showed that we're taking a bit string m, which has v variables, and we're using v qubits to prepare the representative quantum state for that. So what we would like to do is come up with a better encoding f, which is going to go again from a bit string of plus and minus 1s, that is v long, and we want to encode this onto a smaller Hilbert space with less than v qubits ideally. But we need to make sure that, again, that this embedding commutes with our objective function in the same way it did before. Where what I mean by this is that if I apply this embedding to get my sort of encoded state, the state that represents my bit string, and I evaluate the corresponding Hamiltonian that represents my objective function, I should get the same answer, right? So this commutative diagram is showing that whether or not I start from a bit string, evaluate it, and then convert that or plug it into my objective function, and then do the embedding of the objective function, I should get the same answer as if I had just embedded my bit string to begin with and evaluated the embedded objective function. So you can go any direction around this chart and get the same answer. It's kind of what this is representing. And this commutation condition is sort of trivial in the case of QAOA, but it won't be for the embedding that we're going to come up with. So this is going to be an important thing to come back to, excuse me. Okay, so the key idea for how we're going to construct this embedding is using something called quantum random access codes. They were conceived in a very different context than how we're using them here. They came about in the context of communication complexity, and it's not really important for the purposes of this talk to understand why they were invented. But the point is that you can take any single qubit state and represent it in the following way with this block vector, essentially. Where you have some degrees of freedom on the coefficients of these z, y, and x Pauli observables, and they have this normalization constraint. So this mapping that we showed before, F naught, is basically just saying we're going to encode our bit of information, M1, into this variable A, and we're going to set B and C equal to 0 all the time. So that's a fine thing you can do, and again, it leads to a very natural construction. What we're going to do instead is we're going to encode 3 bits of information, one into each of these variables. And this normalization is here just to ensure that this condition over here is met, that the state is normalized. Okay. So again, this is what when you plug these variables in, this is how our embedded quantum states will look in both the embedding used by QAOA and the embedding used in this paper. All right. So before I just breeze past this, I feel like it's worth explaining a little bit about how quantum random access codes work, because it's partially relevant to how we will be sort of decoding these things later on. But the idea is that if you are just given a state and you're told that it's a quantum random access code, a single qubit, then what you're able to do is extract 1 bit of information from this state with probability a little bit greater than 80%, right? So I can sort of choose which of these bits I want to recover and have a better than random chance at just recovering that. And the way you would do this is by measuring this state with respect to the corresponding observable. So if I wanted M1, I would measure the expectation value of my random access code with the Z observable and so on, right? This will be useful later because this is essentially how you can extract these bits of information from your quantum state. It's worth pointing out too that in the initial setting where these came up, they were sort of looking at the situation where you're only given 1 copy, which is why this probability matters here. In our situation, we're going to be able to re-prepare these over and over again. So in practice, we'll be able to extract all 3 bits because we can just measure multiple times, right? It's also kind of nice to visualize that if you look at all of the different states on the block sphere where these quantum random access code states live, they form a nice little cube on the block sphere, which is kind of neat. Gives some good visual intuition about how these things are spread out, right? Okay. All right. So we've successfully constructed an embedding that uses less qubits than we had before. The only thing now is to ensure that this commutation relation is satisfied, right? So one thing I want to note is that basically ensuring this commutation relationship, it amounts to ensuring that this condition here is met, right? Namely that if I take the equation that I had before for how I'm extracting these bits mi and mj and I multiply them, they need to be, this product needs to be consistent with the product here on the left, right? So if, for example, I chose bit M3 and M5, this is true because these Pauli operators here are defined on different qubits. So this product of them just sort of tensors together nicely and everything's nicely behaved. However, if I were to pick 2 variables that are on the same quantum random access code, this would no longer hold, right? And the reason for this is that I'm going to be assigning a different Pauli on the same qubit to each of these. And so these will no longer just tensor together nicely. They will actually multiply. And because Paulis are they're self-inverse, basically what's going to happen is that the product of M3 and M1 will just be equal to M2 because it's just going to give you a different Pauli. There's only one other option because it can't be the identity. And this will just break everything, right? So in order to ensure that our embedding commutes with our cost function, it's important to make sure that no 2 vertices are embedded onto the same qubit if they share an edge in our graph, right? And I'll say more about this in the next couple of slides. Okay, great. If there's any questions in the chat, definitely stop me so I can make sure all this is clear.
Yeah, no problem. No questions so far. We're still good.
Cool. Okay. So how do we ensure that this embedding works? Like, this is a nice statement. Ensure that no 2 edges with the same, no 2 vertices with an edge are assigned to the same qubit. How do you actually do that, right? So the way that we're going to do this is using something called graph coloring, right? Now, this is going to be, let me just review quickly what a graph coloring is. Let's say I have some graph with edges and vertices like this. I want to assign a unique color, or a set of colors, excuse me, to the vertices of my graph such that no 2 edges no 2 vertices that share an edge, excuse me, are the same color. So this one over here on the left, is an invalid coloring because there's two yellow nodes that share an edge. Both of these would be valid, even though this one has two blue nodes. They're not connected by anything, and so that's allowed, right? And what you can kind of convince yourself of if you stare at this is that this is a stronger condition than what we asked for before, right? So if I say that I'm only going to embed vertices onto a qubit if they're the same color in my coloring, then it will be clear that none of those share any edges in the graph, and our commutation will hold, right? However, there's certain situations where this might be sort of over conservative, and we'll look at that in a second, right? It's worth noting, though, that finding the optimal graph coloring is an NP-hard problem, right? So if I was using this strategy I just mentioned, right, where I'm going to only embed vertices onto a qubit if they are the same color, it's clear that you would prefer this coloring down here over the one in the middle, because this would tell you that every vertex needs to go on its own qubit, and your embedding would have no savings in space, whereas this one would essentially only need 3 qubits, since these two blue ones could go and share, these two blue nodes, excuse me, could share a qubit, right? However, we don't actually really need to solve this optimally. There's some pretty good heuristics that you can do, which run in polynomial time, polynomial in the number of vertices. And they're guaranteed to find a number of colors, which is basically one more than the maximum degree of the graph, where degree is basically the maximum number of edges that leave any one node. So in this case, the degree would be 3, right? Okay. So in practice, this is what we use in the paper to find these colorings. Cool. And one thing that's worth pointing out, though, is that although the graph coloring sort of ensures your commutation holds, it's not a perfect representation of what you actually care about if you're trying to maximize your compression, right? That maximize the number of bits, number of vertices that you can represent with the fewest number of qubits, right? So as sort of an illustrative example, this graph is 4 colorable. You can prove that, and I manually checked that there's no way to color all of these nodes with 3 colors such that adjacent nodes are the same color, or are always not the same color, right? So if you kind of look at this, I've just sort of reorganized all the nodes over here and looked at how you would lay these out on qubits. You know, naively, this is an optimal solution to the graph coloring problem. So again, this would be the one that, you know, even the best case scenario where you get a perfectly satisfied graph coloring where you're optimal, it uses 6 qubits, right? And you can see that there's a lot of waste here. We're using 3 qubits that we basically get no space savings on, excuse me. Whereas you could actually come up with a non-optimal coloring, which has 5 colors instead of 4, that actually does better, right? And so, like, graph coloring is sort of an over-strong condition, right? It doesn't really capture precisely what we care about, but it will make sure that your cost function doesn't break. And it's worth noting that you can actually do even better. So there's another 4 coloring that actually does let you get away with only using 4 qubits, and you get an approximate or a compression of 2 3/4 vertices per qubit, right? So this would be like the space savings in how big of a problem size you would actually be able to run with a fixed size quantum computer. Okay, so I think we're nearly in a position to state the full progression of this algorithm. I know there's a lot of background building up to it. So given some input graph, first thing we're going to do is try and color it, right? Taking into account the things we just mentioned, that you might need to do some pre-processing after your coloring and try and get a little more savings in your space. This is going to allow us to embed our problem into a Hamiltonian, where again, we're going to be doing something very similar to how we took this MaxCut objective function and converted it into a Hamiltonian, where we just replaced it with these Pauli Zs. We're just going to be replacing them with other Paulis. And the fact that we're using this coloring to make sure that none of these pairs of Paulis are on the same qubit, right? Once we have this problem, we're going to try and approximately find the ground state of it, right? I say approximately because this isn't a thing that you can do efficiently in general. But we're going to show that heuristically, maybe you don't actually need to solve this optimally in order for this whole technique to work. And then once we have this approximate solution, which I'm going to call rho relax, we need a way of extracting some final solution M. Ultimately, we need a vector of plus and minus ones that specify our solution, our coloring, of this original graph. And we're going to try and show several methods for extracting that from row relax. So we're going to call this quantum rounding, because
We
you can kind
have
of
a
think of
couple questions now, Bryce. Sorry, didn't mean to
perfect. Yeah,
interrupt
yeah.
you.
No, yeah.
Um,
Let's hear them.
so first one is there a limitation of embedding bits into the qubit?
Yes, if you have a graph that is fully connected, for example, you will get no savings in space, essentially, because you won't be able to find any pairs of bits that are allowed to share a qubit, right? As you reduce the connectivity of your problem, the embedding starts to become more and more efficient. But in general, yes, there are restrictions.
Yeah. Next question is, do the number of required qubits for embedding increase with the density of the graph?
Yes, also yes. So that's very similar to the previous question. But it's also kind of worth noting, right, that the hardness of MaxCut is directly related to the density of this graph, right? So it's known that 3 regular MaxCut graphs are sort of the maximally problematic size, right? Where and then as you start having graphs with more and more connections per node, they actually become easier to solve in practice. So this is kind of good for us because it shows that the graphs where you would expect to do the best on compression are actually the ones that are the hardest to solve in general. And so if you had one of those graphs that they're referencing where it was nearly all to all, you would probably be fine to just use a classical heuristic and solve that there. You might not need to try a quantum heuristic to see if you can do better.
All right, thanks, Bryce.
Yeah, absolutely. Okay, so I'm not going to say much about step 3, right? The problem of approximate ground state solving is pretty widely covered in other places. We're going to use VQE for this, but there's other algorithms that you could use that produce approximate ground states. Really, the interesting bit that differentiates this technique from prior quantum optimization algorithms on near-term hardware are steps 1, 2, and 4. So I'm going to jump straight to step 4 and talk about, given some state, how are we actually going to extract solutions to our original problem from that? Cool. Okay, so the problem setup is we're given multiple copies of row relax, or alternatively, just the ability to prepare it over and over again. And we need to somehow pull out a bit string M, which we are hoping is close in objective value to the optimal solution, which I'm going to call M star. And again, M star is not known. This is really what we would like to estimate. So the first method is called Pauli rounding in the paper. In the implementation of this, which I'll sort of plug later on for the prototype, it's called semi-deterministic rounding. But the idea is just to use this fact from whenever I was just describing quantum random access codes and say that, okay, if I can prepare these things over and over again, I'm just going to treat these states as though they are quantum random access codes and try and extract these bits M, MI, MJ, MK from there, right? So it's worth noting that the state row relax won't actually be a proper QRAC state, right? It's not going to be constructed of the form that we showed before. So that's why we have this sort of sign function here, because I'm not going to actually get a plus or minus 1 from this. I'm going to get something that is like plus or minus around 0, and then I'm just going to threshold that. If it's less than 0, I'll call that -1. If it's greater than 0, I'll call that +1, right? And this is a very natural way to go about this. However, there's another method that we showed, which is called magic state rounding, very provocatively named. And this one is a little bit more interesting in some ways because it comes with some extra guarantees on performance, right? But the idea here is that we are going to project our state row relax onto the image of this embedding, right? In other words, we are going to project it onto a valid QRAC state and then measure that QRAC state, right? And part of the challenge with this is that there's 4 different ways that you could measure each qubit, right? And that's kind of represented by these diagonal lines, right? Again, remember that all of these QRAC states sort of live on the edges of this cube, which is sort of, you can see the diagonals of. And so each measurement, I'm going to have to pick one diagonal and say, is it this one or the one that's just on the opposite side of the sphere, right? And so there'll be some probabilisticness in how I choose these bases here. All right. So empirically, Pauli rounding actually seems to perform very well. It's kind of unfortunate that it doesn't come with any like analytical bounds on the performance of it, but it seems to hold up pretty well, even though there are situations you can construct where it should fail. We just didn't end up seeing them very much. Magic state rounding, on the other hand, is a more complicated story. So it has this bound, which I'm going to explain, but it's important to note that this is a conditional bound on the performance, right? So if it happens to be the case that the relaxed solution you get has an energy which is greater than the optimal discrete solution, then you have this bound, right? So in other words, let's say the max cut of some graph I have is 20. Whenever I embed this into a quantum relaxed version of the problem, it might be the case that I can come up with relaxed solutions to the problem that get a score better than 20, right? It can sort of exceed the optimal answer of the original harder problem since I've relaxed it, right? This might be analogous to the knapsack problem, where if you can cut up all these boxes, you can always fill the truck up all the way. But if you have to do discrete packages, you might not be able to actually fill the truck perfectly in practice. The optimal answer might be less than the relaxed answer, right? So if you happen to get a relaxed solution that sort of lies in this intermediate regime where it exceeds the optimal solution for the hard problem, the original problem, but it's not quite like the perfect relaxed solution, then you get this bound on performance that you will be within 5/9 of the optimal answer, right? And this is less than something like Gomez-Williamson. It's a classical algorithm that comes with an approximation ratio for MaxCut. I think it achieves something like 0.86. But we were very excited about this because there's not a lot of techniques that have any sort of approximation ratio guarantees like this, even though this is conditional, right? And one other thing that's worth mentioning here is that the better your relaxed solution is, the better you would expect this approximation ratio to increase, right? So it sort of motivates that even if you have some solution to the relaxed problem that you think is better, you think it has this guarantee, if you can ever find a better relaxed solution, you would still expect it to give you better answers whenever you try and round it to the original problem. Right? So over here on the right, I have one of the figures from the paper where I'm basically just taking the optimal relaxed solution. So I haven't approximately solved it. And I'm just rounding it with both of these techniques to look at the distribution of outcomes that you get, right? And so this burnt orange distribution is the magic state rounding. So the best case scenario would be that everything's clustered around 1, which means that when I round my solution to get a bit string, it's the optimal bit string every single time. And you can see that these blue histograms, which are the Pauli rounding, they tend to do better empirically than the magic state rounding, even though the magic state rounding sort of has a bound on performance. You'll note that you see some noise around here, around 0.5, which again is sort of indicative of the fact that Pauli rounding doesn't actually have any sort of analytical guarantees on how well it will perform. Even though it seems to do well in practice, you can show that there will still remain some number of cases where it sort of fails. Okay. Are there any questions before I move on, Olivia?
Yeah, there are. I was just waiting for a good time.
Cool.
One person said, how is 4 coloring the best for the graph you showed earlier? Doesn't 3 coloring state that you can have any color, any graph with minimum 3 colors? I'm not sure I understand the question.
No, that's not true. It's
Okay.
known that for any planar graph, you can 4 color it. I mean, I brute force checked this last night just to be absolutely sure. It's like 170,000 configurations, which you can do on a laptop still, and you can show that there's no way to 3 color this. I invite you to try, and I would love to see the solution.
All right,
yeah.
sounds good. And then the next one is, oh, I think he was trying to answer the question above him in the chat. Okay, I think we're good now.
Cool. All right. Okay, so again, this figure here is just sort of highlighting the performance of our rounding schemes. But again, we're sort of assuming we have access to the perfect relaxed solution. And like I said earlier, this problem we've relaxed to is not actually easier than the original problem. It's just different. And so, it's sort of a big question, like, can you actually produce relaxed solutions that achieve this approximation ratio and still get good performance? So we ran this algorithm both in simulation and on hardware. So these this is sort of the x-axis here is the number of iterations that we trained VQE. So what you're seeing is the performance of the relaxed solution as it gets better and better, and the algorithms tries to get to the optimal answer. This black line is sort of representing the optimal discrete solution, which, you know, in practice wouldn't be known, but since the problems are small enough here, we can know it. And this red line is the best possible energy that you could get, or the best possible objective value you could get for your relaxed problem. So you'll notice the simulations extend further than the hardware runs, just because running these circuits on hardware is very expensive. But you'll see that all 6 of these different simulations get within this regime where our approximation ratio kicks in, even on hardware. And then over here, what you're seeing is sort of a visualization of the results of rounding, right? So whenever I take the final state obtained from this run, you know, I get something that's well close to the optimal relaxed solution. And then you look at this green distribution, it's showing you the values that you obtain whenever you do magic state rounding on this, right? So I measure in the magic state rounding procedure many, many times, and I get some distribution over outcomes. For Pauli rounding, you just get one outcome, because again, I'm going to be taking an expectation value over the particular binary variables. So I take many, many shots, just like magic state rounding, but I'm using all of those measurements just to get one bit string. Whereas for magic state rounding, each measurement is its own bit string, if that makes sense. And you can see that these perform pretty well. So the optimal solution is 20. This green curve, which gets close to the optimal relaxed value, achieves the optimal answer for Pauli rounding. And it's hard to see, but there's a little green dot there too, that magic state rounding samples it sometime as well. Cool. And then, so one thing that was important to me when we were working on this is trying to understand how close you have to actually get to this optimal relaxed solution in order for rounding to perform well. Because if you have to get extremely close to the optimal answer before rounding starts to perform even decent, then that's a real problem to making this work in practice, right? Because we know, again, that this relaxed version of the problem is a very hard problem. So what we would like to see is that even just approximate solutions to the relaxed problem perform well in practice. So that's what this chart is. So I've taken this green curve here, and it's now the only one on the plot, right? And what I'm showing is sort of the tails of the distribution if I were to round at different points during this execution. So in other words, this whole thing runs for about 10,000 iterations of training, but if I had stopped it after 100 and rounded, I would have gotten a Pauli rounding solution of something like 17. You could see that after 10 iterations, there was a tiny chance of the top 0.2% of solutions were sampling something close to the optimal value. And of course, as you get better and better relaxed solutions, the distributions tighten around the better answers. But this was encouraging to see. What would have been maybe less encouraging was that these answers are pretty terrible up until the very end, whenever we get within this like close range of the optimal solution for the relaxed problem. And then suddenly they become good. So again, like the heuristic idea with this is that in practice, we might be able to only get decent solutions to this relaxed problem and still round those to acceptable solutions for the original problem. Are there any questions on this one, Olivia?
Not from the chat. No, I don't think so. But I am having a little bit of a hard time just understanding this graph here on the right a little bit. So
Yeah.
maybe we could just spend like just another 3 minutes on it.
Yeah, absolutely. So basically, so this chart on the left here is what these distributions are showing the results of rounding at the very end of VQE,
Yep.
right? And this is showing something similar. However, instead of plotting the full distribution, which would have just been far too much data here, I'm sort of taking just the top, like for example, the top 5% of samples that I observed and plotting those, right? And so
Oh,
you could imagine it as though like this, like first of all, you don't need 6 of these stacked next to each other to the right because there's only one run that I'm looking at.
right.
And I've sort of staggered them throughout the training. And the idea is to kind of try and understand if I had not trained all the way to this, you know, very good final solution, would I have still done okay if I had rounded earlier on, right? And this is basically just trying to get at, you know, how robust is this rounding procedure to errors in your relaxed solution.
Right. So when you were talking about the graph here on the right, and you said this wasn't very good until later on in the iterations, you were talking about the Pauli rounding, the
Oh, so
x-axis that I'm looking at here.
yeah, so the Pauli rounding does perform pretty poorly, but I was actually saying that would be what you wouldn't want to see. Like we were hoping to not observe that it performs bad until the end, but it actually seems to perform very well until the end. Like even after, so again, this is a log scale on the x-axis. So even after like 10 iterations, there was a chance of sampling a solution that was very close to the optimal answer.
Okay.
Again, these are small problems for now, but still encouraging.
Okay. Yep. Thanks for clearing that up.
Yeah, absolutely. Okay. So this is a very similar plot. However, it's for a 40 node MaxCut problem. We did this on the IBM Dublin quantum processor. And the best observed sample that we got had an approximation ratio of 0.905, right? And so in other words, it was like 90% within of the 90% of the optimal solution, right? We were very proud of this. This is, as far as we know, the largest optimization problem run on hardware to date. The previous largest at the time of writing for this paper was from the Google group. So they ran a 22 node, 3 regular MaxCut graph, and I believe they achieved a lower approximation ratio. There's recently been 27 node MaxCut graphs that have been run from the IBM group. These were hardware native graphs. They were tailored to the specific device. So yeah, this sort of compression we get in the number of qubits allows you to extend to much larger problem sizes, which is nice because you start to get into a regime where maybe finding the optimal answer isn't quite so trivial. Cool.
We had a question, and I think it was from the previous slide. Sorry, there's a little bit of a
Cool.
delay.
No, that's okay.
The graph on the left, does it seem that depth 2 in blue crosses the optimal binary solution bound faster than depth 9, although depth 9 reaches a higher value? Can you explain?
Depth 2, so he's talking about the depth 2 experiment versus the depth 9 simulation, or, oh, I see.
Um,
So he's talking both about the simulations.
yes, I think
Yeah,
the blue simulation, the light blue one.
yeah, so I mean, these are just like single examples of running these things on hardware, so or on simulation, right? So they're not averaged over many examples, which is might be something you'd be interested in. So there's a couple things that could be going on there, right? So when you have a deeper ansatz that you're using for VQE, you have more parameters, and that can make it harder for your classical optimizer to find good solutions because it's a bigger space it has to explore, even though in principle it can find better solutions in that space because the ansatz should be more expressive. It's the story's a little more complicated in this situation, right? Because we know that the optimal, or actually, yeah, sorry. I was going to say that the optimal solution to our original problem is a product state, but the optimal relaxed solution need not be. So I stopped on that. But yes, there's some amount of noise in the training of this. So you can't read too much into this.
Mm-hmm.
But at a high level, like there is usually some kind of sweet spot where, making your ansatz deeper and deeper and deeper might make your solution better if you can run for extremely long periods of time, but it might also slow down the training just because you have so many parameters to deal with.
It's a balancing
There's
act.
there's a lot to be said on that, and you get into like over parameterization and stuff like that. But at a high level, I think that's one takeaway you could have from this.
Okay.
Cool. All right, so I think I already talked about this slide. Unless there's more questions, I can come back to it if there are.
I don't think so. I think we're good to, yeah,
Okay,
conclude.
so this is the conclusion of the first and largest part of the talk, right? So the key takeaways is that we show that there's this rigorous connection between the eigenvalues of this relaxed Hamiltonian we construct and the rounded solutions to our original problem, which is interesting, right? This sort of process of using quantum relaxations can save you a lot of space on your quantum computer and can therefore let you access much larger problem instances than might have been possible previously. And we know that this relaxed problem is itself very hard. However, there's sort of heuristic evidence that we don't actually need to solve it to arbitrary precision in order to get good rounded solutions out of it. There's lots of future directions for this work. So we just look at one class of quantum random access codes, but there are others where you might encode some number of bits into 2-qubit states. This can get much more complicated. It's also interesting to try and seek out classes of problems where you might be able to show, at least empirically, that this gap between your optimal discrete and optimal relaxed solution is extremely big. That might indicate that you have a higher chance of getting better and better solutions and be able to push your approximation ratio up. And there could be much more sophisticated rounding procedures that people could come up with, right? So we just tested two that were somewhat natural to us, but you could, for example, bias your choice of which magic basis to measure in using some other information about the problem. And in fact, there is a working prototype of this that was released recently from IBM Quantum. It's publicly available. It has the implementation of this algorithm in it, and so there's actually a different rounding procedure that wasn't used in the paper that is available there. So I encourage everybody to go pull that down and use it, and tell us if you find anything cool. How am I doing on time?
You're pretty good on time. We're at 12:42.
Okay, cool. The next part of the talk is much shorter, but I wanted to kind of give you an idea of the application that we applied this to, right? So we worked with Boeing to look at how this technique could be used for optimization problems in aerospace design, right? So specifically, there's this problem called ply composites, right? You can imagine that Boeing is making airplane parts out of many layers of different kinds of like plies is what they call them, like sheets of some sort of material. And they have a machine that, given some specification, will go and lay down sheets in different places, and they have one of four orientations, right? So the sheets of whatever material can be oriented at 0 degrees, 90 degrees, or 45 and negative 45 degrees. And I'm sort of just showing like a cross section, but you would imagine that each of these lines is like a two-dimensional sheet of some sort of like fabric or composite material of some kind, right? And it's important to note that when these are laid down, there's going to be some gaps in between. So ultimately the size of the like resulting object will taper and have different properties. And it's sort of known that the way in which you layer these different orientations will result in different overall properties for the larger piece of whatever you're building, whether that be an airplane wing, right? So they're concerned with things like how to use the fewest number of plies while making sure it's strong in certain directions. And there's also lots of other considerations they take into account about how to make sure that the plies don't come apart. And so they have sort of lots of design rules around this. Some of them are sort of make sense from first principles, and some of them are sort of just ad hoc rules that they've observed in practice lead to bad composites, right? But this is sort of the framework that we're going to be looking at. This is where the problem comes from, right? And when I refer to something called a stack, I'm going to be referring to one like vertical section of this plane wing, right? So I've kind of chopped it up into discrete chunks. This would be like an example of a specific stack, right? So up here, it would look like this. Cool. So there's lots of design rules for the full version of this problem that Boeing uses. We were looking at a restricted version because there's a non-trivial step of figuring out how to formulate this on a quantum computer in a way that's makes sense with the resources you have, right? So, for example, you wouldn't want an optimization problem that comes from this to have all-to-all connectivity, because then the technique that we would like to use wouldn't be applicable, right? The embedding would not get any sort of savings in the number of qubits, right? One of the things they care about is the number, like the percentages of different orientations, right? So sometimes it's reasonable, they would just say, okay, the number of 90, 0 degrees, 45 degrees, and negative 45 degree plies within any specific stack should be roughly equal, right? And it's not possible in general to satisfy all of their constraints, but they're trying to satisfy as many as possible. So getting as close to these target percentages as they can is really their objective. There's another one that's kind of interesting, and it was useful for how we were modeling the problem, which is that regardless of how separated they are in the stack, you want negative 45 and 45 degree plies to be staggered, right? So there could be some number of 0 and 90 degree plies in between, but the stack on the right would be preferable to them compared to the stack on the left, right? I think they have reasons for this, and some of them are just sort of empirical observations that certain things work better and have better performance, right? They also have a number of they call disallowed substacks, right? So for example, there would be like disallowed 3 stacks where they say, okay, we want to minimize the number of times that you ever see of any stack within this wing where you have 0, 90, 0. And sometimes they have like up to 4 stacks where they would say, like, if you have 4 zeros in a row, that's bad, right? And sometimes these have like relative importances, can get very complicated, right? So for us, we looked at a sort of restricted version of this problem, where I'm going to say the angle of each ply, I'm going to represent with 2 bits, right? So 2 bits gives me 4 options. And the reason I choose these is because what we're just going to try and look at is penalizing where adjacent plies have a difference of 0 or 90 degrees, right? So this is one of their important sort of constraints that they would like to satisfy as much as possible, right? So in other words, I don't want to see 0, 0 plies. I don't want to see 0, 90 plies, 45, 45, or 45, negative 45, right? I would like for everything to be offset by 45 degrees when you go for between adjacent plots as much as possible. And you can kind of convince yourself that it suffices to ensure that adjacent plies have a different bit in this second bit right here, right? So you can see that if both of them are 0, then it means that you either have a 0, 0, a 0, 90, a 90, 90, or a 90, 0, and all of those are disallowed, right? So this is how we're going to formulate our much more slimmed down version of their larger objective, right? This is the equation that you get if you sort of try and model this. And again, we're using binary variables here, but if you, I'm actually gonna, if you switch to plus or minus variables, then you can see that this is actually just a weighted version of our MaxCut problem, where it's sort of the same thing we saw before, but now we have that some of these edges have more or less importance to them. And the weights are going to be basically proportional to the surface area of how far these plies touch, right? So if I have 2 plies that are next to each other for a very long stretch of the wing, then I'm going to care more if they violate this constraint than if they were to, say, touch in a much smaller place, like this red constraint over here. This is sort of how we generate the problem instance. Cool. You can sort of look at this in a few ways, right? There's nice ways of visualizing this problem. So again, we can think of this as a weighted MaxCut problem. You can see from this objective function that it's very similar to the one we had earlier, although I was saying that some of the edges are more important. You can represent it as a graph, where now I've sort of changed the width of these edges to represent the weight. In other words, like how much they're penalized whenever we cut them, right? So in this case, we're actually doing not MaxCut, but it's MinCut, because these constraints, these edges correspond to violations, and we want to cut the fewest number of them as possible, right? That's kind of the idea we have here. Does that make sense to everybody in the chat? Cool.
I think so. I think we're good.
All right. So this is a familiar plot now. We run the same problem on quantum hardware. Again, this is a 40 node problem, so same size as the one we showed earlier. The fact that it's weighted actually makes the problem easier. So I think unweighted 3 regular MaxCut would be the hardest. This graph has much more. It's not 3 regular. It has more connections, more dense, and so you get the problem itself is a little bit easier. You'll also notice that the y-axis here is much larger. That's because each edge no longer just counts for 1. Some of them count for 20 or 40 or up to large numbers. And we observe that we get some rounded solutions that are very close to the optimal answer. So you can see that this one here in particular gets very close. And this is actually how you can visualize the solutions, right? So here I've highlighted the edges that ultimately get cut in the best found solution, which got an objective value of 617. The optimal solution got an objective value of 641. So I think that's like 0.96 approximation ratio. And similarly, you can look at this full plane wing and try and highlight the interfaces between edges which violate a constraint. So what you would like to see is that you have the fewest lines possible. The more and more dense this diagram would be down here, that would be indicating that you have violations more and more spread out through your wing. So this optimal answer is maybe a little bit less populated, but not much. We're pretty close to it. So we were very happy with this. Okay, so ultimately, the takeaway from this is that we have a novel formulation of the ply composite design problem. It reduces the weighted MaxCut, but there's plenty of room to generalize this and add in some of the other constraints. We came up with a lot of formulations along the way. So it was sort of just a starting point for figuring out the best way to model these kinds of problems on quantum hardware. And we were able to use this quantum relaxation technique in order to get an approximation ratio of 0.96 on a 40 node problem, which it's worth noting that like the practical sizes of these problems that Boeing solves are somewhere between like, I think they quoted like 60 to 200-ish plies. Like we're not crazy off in terms of the problem size, although the types of constraints that we actually take into account are much less sophisticated than the ones they do. So if we could continue to increase the problem size just a little bit and also make the objective function take into account these more complicated kinds of constraints, then you know, that would be pushing things in a direction which might be useful at some point. Yeah, and I think I kind of summarize these. There's lots of ways of extending this. You could look at non-uniform target percentages, take into account some specific disallowed stacks, or use local Hamiltonians, which have more than 2 terms, right? So that would correspond to like hypergraphs or things like that. All of these are fruitful areas for further exploration. And yeah, that's mainly what I have to say. If there's any more questions, we can discuss. But
Thanks,
yeah.
Bryce. That was great. Yeah, we've had a pretty lively chat the whole time. I wanted to ask, because I always like to ask this. I know you listed a couple future directions, but do you have a plan for like the next thing you're going to do, like immediately following this work?
It's a good question. I think extending this to take into account different kinds of QRACs would be very interesting. So, you know, the actual bound that we have on the approximation ratio very much takes into account the fact that we're using QRACs on 1 qubit states. So it would be interesting to see if that can generalize. But even if the using like larger QRACs doesn't result in any sort of analytical guarantee, what we observe is that the Pauli rounding actually performs better anyway. And so it might just be the case that you lose this guarantee on the performance of your algorithm, but you might be able to get higher compression and still recover some good performance by using higher weight QRACs. So that's an interesting area for further research. And also, I think it's worth looking more into these different kinds of the rounding schemes. You know, we included 2 in the paper. Came up with all kinds of different variants of these along the way. That were, you know, you could come up with really ad hoc ones that seem to work okay. So that's like it's definitely not the end of the road on that front either. I think there's room for people to make further strides there.
Another question, when you're running these types of experiments on real hardware as opposed to the simulators, have you studied what particular type of error is hindering your performance most?
It's a good question. Actually, no. So one of the things I was most surprised about with these results is how well they performed, even with relatively few like error mitigation techniques being applied,
Yeah.
right? Like we used a relatively short ansatz to prepare these relaxed solutions. I used a little bit of readout error mitigation, but nothing like too sophisticated. There was no zero noise extrapolation or like, you know, gate level error mitigation. And I think that there's some really interesting ideas for how these relaxed solutions could be generated without using variational algorithms. I mean, certainly in the presence of a fault-tolerant quantum computer, there's more techniques you could use to get ground state approximations that would be really interesting. But like that piece that I kind of skipped over of how you're getting the relaxed solution there's like a ton that can be said there, just more than I could really cover here. And since it wasn't really the focus of the paper, we kind of like spent more time on the encoding and decoding piece. But there's really a lot more that could be, you know, pressed in terms of, you know, extracting performance from that.
Yeah, okay, that's super interesting. Because I would have naively assumed that a lot of error mitigation would have to go into this to get those results. But yeah, that looks really cool. And so you guys didn't have to implement any type of like dynamical decoupling in the algorithm? Okay, awesome.
No.
Neat. Okay. Um, Another question. I don't know exactly what this means, but could you apply the quantum Hamming code to this rounding solution? Do you know what that means, Bryce?
The quantum Hamming code. I think he or she is referring to different kinds of embeddings of like how you're representing your your states. Yeah, it's not really clear to me exactly what they mean.
Okay.
If they can rephrase, I'd be happy
Yeah,
to
if you
circle
want to
back on it.
rephrase what you mean, we can try to clear it up. Sorry, I'm just having a little trouble understanding what you're trying to
Like
ask.
maybe saying, or here they're saying that after you get a solution back, you could check other bit strings which have like low Hamming distance away. Like, so in other words, like try flipping individual bits and see if you can find a solution locally that's comparably good. We didn't try that. It's not obvious to me that would necessarily work well, but you can pull the prototype down and try. Like, all the code that I used for this paper has been polished and put into that prototype. And it's very extensible to implement your own rounding solutions and things like that. So I would
Yeah, if we have a link
very,
for that, we could share it in the chat, or we
yeah,
can put it in the description too, if anybody's interested in that.
absolutely. Yeah. I can send a link and we can put it into the description stuff. But if you just Google prototype-QAOA, it's in the Qiskit community repo. I'm
Great.
sharing my screen right now, so I can't get the link for you right now. But yeah, it's publicly available, and we would love your feedback.
Yeah, we love open source contributions, and I think the prototypes team is doing some really, really important work with getting that out into the open. So, on my team, thank you on behalf of, what your
Yeah,
team is doing.
absolutely.
Um, I think that was sort of the end of the questions. People have been very complimentary in the chat. I know you can't see it, Bruce, but people have said this has been a really, really illuminating talk. So thank you again for sharing this with us.
Yeah, I'm glad. Thank you all for coming.
All right, I think we are good to wrap up here for today. So if you liked this talk by Bryce, who again is one of our internal researchers, feel free to like and subscribe. And we do these types of seminars every Friday at noon. This one has been particularly fun. So again, thank you so much, Bryce, for joining us. And have a great holiday weekend, and we'll see you all next Friday.
It's been a pleasure.